Hey everyone, and welcome to another Forge College Explainer. Today, we're cracking open the engineering blueprints for mastering multi-program interactions on Solana. Specifically, we're diving into the patterns and principles for cross-program invocations. Look, if you're building in Web3, you already know that composability is basically the superpower of blockchain development, right? But actually getting different programs to talk to each other, seamlessly, securely, and without blowing up your compute budget, well, that requires a deep understanding of the architecture. And that is exactly what we're going to unpack today.
So let's anchor ourselves for a second. In our previous lesson, we went deep into debugging custom templates and best practices, right? You practice validating that client-program interactions actually matched your expectations after you made template changes. But what happens when your program needs to talk to another program? We're shifting our focus today from a simple, single client-to-program relationship to the fascinating and, honestly, sometimes a little dangerous world of complex program-to-program coordination. When your code is executing autonomously to call another contract, the stakes get higher, the security requirements get way stricter, and the design patterns you choose become absolutely critical to your app's success.
Okay, so here's our agenda for today. We're going to start with a welcome to CPIs, move into the function call model, check out 3 essential CPI patterns, look at invocation ordering trade-offs, and then wrap it all up with a summary and next steps.
Let's jump right into Section 1. Welcome to CPIs, the basics of internal communication.
Okay, so we hear the acronym CPI thrown around constantly in Solana development, but let's demystify what's actually happening under the hood. A cross-program invocation, or CPI, is a synchronous call that a Solana program makes to another on-chain program right in the middle of instruction execution. I want you to think of a CPI like a highly efficient, high-speed office environment. Instead of sending an email out into the void, waiting hours for a response, and dealing with massive network latency, these programs are literally handing clipboards of data back and forth to each other across the desk. It's immediate, it's synchronous, and it keeps the whole operation moving seamlessly. There's no waiting for the next block to be validated. The communication happens right then and there, within the exact same slice of execution time. And the mechanical difference here is actually really striking. Unlike an external, client-issued transaction that spins up a completely new execution context, a CPI is entirely internal. It shares the exact same runtime execution environment, it pulls from the exact same compute budget, and crucially, it relies on the exact same atomicity guarantees. Now, atomicity is just a fancy way of saying all or nothing. If program A calls program B, and program B suddenly hits an error and panics, well, the entire transaction, including everything program A just did, rolls back as if it never even happened. You are bound together in the same compute budget and the exact same fate.
Moving right along to Section 2, the function call model, looking at parameter qualifiers and invariants.
If you want a foolproof way to reason about this without getting lost in the code, just picture a CPI as a standard programming function call. The accounts you pass, those are simply the arguments. The AccountMeta entries act as parameter qualifiers, basically declaring whether an account is read-only or mutable. The calling program passes these memory references to the callee. And the receiving program, the callee, acts like a super strict bouncer at an exclusive club checking VIP passes. It absolutely doesn't blindly trust the caller just because they're another program. It rigorously enforces its own invariants by aggressively inspecting those accounts.
So how are those VIP passes actually evaluated? The callee basically asks 2 main questions. Step 1, checking the writable flag. Is it actually safe to mutate this state? Step 2, checking the signer flag. Is the caller actually authorized to act? Passing a read-only account when a mutable one is required is essentially like handing a permanent marker to a toddler who is only supposed to look at the wall. It's a massive violation of the contract, and it's going to result in an immediate runtime failure. If you try to tell a vault program to transfer tokens out but you forget to provide the proper cryptographic signer flag, well, that strict bouncer is going to throw you right out of the execution layer. No exceptions.
All right, let's hit Section 3, 3 essential CPI patterns. We're talking delegation, orchestration, and proxy.
Now for the real meat of our blueprint. These 3 patterns dictate how your code will actually flow and interact with the wider Solana ecosystem. Notice the stark trade-offs here regarding who actually does the heavy lifting, your client application sitting off-chain or your program living on-chain. The client burden shifts dramatically from high in delegation down to low in orchestration, all the way to minimal in the proxy pattern. These aren't just arbitrary styles, guys. Choosing the right pattern here will literally define whether your application is a joy to build front-ends for or a total nightmare. Let's unpack each of these individually to see exactly how they work in the wild.
First up, we've got the delegation pattern. In this setup, your top-level program acts as a very thin dispatcher. It takes the accounts supplied by the client and essentially just forwards them to a well-known utility callee. Now, this delegation is absolutely fantastic for composability with standard programs like the token program. But, and it's a big but, it places a massive burden on the client application to get the account lists perfectly right. If the client forgets one tiny account, the whole call fails. Imagine asking a user or a front-end interface to manually construct and approve 15 different routing accounts just to swap a single token. Yeah, that's the heavy delegation burden in action. You gain ultimate flexibility, for sure, but your front-end engineers will be working overtime to ensure they're passing the exact right array of accounts in the exact right order.
Next up is the orchestration pattern. Here, the caller, which is your program, centralizes the responsibility. It derives program-derived addresses, or PDAs, to act as signers via the invoke-signed convention, and it invokes multiple callees in sequence. Orchestration is your absolute go-to for complex coordinated actions. Let's say you're building a decentralized lending protocol. When a user deposits collateral, your program needs to take their tokens, update a decentralized ledger, mint a receipt token, and emit an event to a tracking program. With orchestration, the program takes on all that bureaucratic headache of assembling the accounts so the client doesn't have to. The client just hands over a few simple identifiers, and your program handles the complex multi-step orchestration perfectly on-chain.
Finally, we have the composite or proxy pattern. In this model, the caller acts as a high-level API gateway. It completely hides the internal complexity owning most of the accounts itself and requires absolutely minimal inputs from the client. Think of the proxy pattern as the ultimate encapsulation tool. Let's say you're building a Web3 game. The user simply hits a level up button on their client app. That's it, one single input. But on the back end, your proxy program securely handles 10 different internal NFT and token accounts, upgrading stats, burning resources, and validating achievements. It provides a beautiful, simple, clean interface to the client, while strictly controlling authority on the back end via transparent PDA derivation schemes. It's incredibly user-friendly and highly secure.
Section 4. Invocation Ordering Tradeoffs. It's time to talk about atomicity versus compute limits.
Look, architecture doesn't exist in a vacuum, right? It has to survive the physical constraints of the Solana network itself. Unfortunately, we don't have infinite computing power at our disposal. Every instruction we execute consumes the specific slice of resources. The reality of network constraints becomes glaringly obvious when chaining these operations together. A single CPI? Low compute. A short sequence? Takes medium compute. But a long chain? That requires high compute and risks hitting hard network limits, like the maximum compute unit cap per transaction. While sequential CPIs give you the absolute superpower of atomicity, meaning if one action deep in a 10-step chain fails, they all instantly roll back to protect user funds, chaining too many together acts as a massive drain on your single transaction's shared compute budget. You always have to balance that incredibly powerful atomic guarantee against the hard performance limits of the runtime. If you design a proxy pattern that calls 20 other programs, you might just find your transactions failing simply because they ran out of computational gas.
Let's bring it home with Section 5, Summary and Next Steps, wrapping up the blueprints.
Okay, let's step back and look at the big picture takeaways from today's schematic. We've covered a lot of ground, from basic mechanics to advanced architectural trade-offs, so let's distill it down into actionable wisdom. Here are your non-negotiable golden rules. Pay close attention. Number 1. Mismatched AccountMeta flags are the leading cause of runtime failures. Guard your read-only and signer privileges carefully. If your program expects a signer and the client sends a read-only account, boom, the transaction dies immediately. Number 2. Explicitly choose your CPI pattern based on the desired balance of client burden and program coupling. Remember, delegation for composability, orchestration for coordination, and proxy for encapsulation. Don't just stumble into an architecture. Choose it deliberately. And number 3, always document your account expectations clearly to prevent long CPI chains from breaking. Map out exactly who provides each account and who must sign before committing any template changes. Up next in this module, we'll be tackling designing CPI instruction flows. But before we jump into actually designing those concrete flows in the next lesson, consider checking out the Forge College website at forge.college to deepen your Web3 expertise and explore even more resources. As we wrap up this explainer, I want you to ask yourself a critical question. Look at your current projects. Which of these 3 patterns is currently dominating your codebase, and is it secretly killing your composability? Think about it. Thank you so much for joining me on this Forge College presentation, and I will see you in the next one.